In mathematics, a spherical coordinate system is a coordinate system for three-dimensional space where the position of a point is specified by three numbers: the radial distance of that point from a fixed origin, its polar angle measured from a fixed zenith direction, and the azimuth angle of its orthogonal projection on a reference plane that passes through the origin and is orthogonal to the zenith, measured from a fixed reference direction on that plane. The radial distance is also called the radius or radial coordinate. The polar angle may be called co-altitude, zenith angle, normal angle, or inclination angle. The use of symbols and the order of the coordinates differs between sources. In one system frequently encountered in physics gives the radial distance, polar angle, and azimuthal angle, whereas in another system used in many mathematics books gives the radial distance, azimuthal angle, and polar angle. In both systems I is often used instead of r. Other conventions are also used, so great care needs to be taken to check which one is being used. A number of different spherical coordinate systems following other conventions are used outside mathematics. In a geographical coordinate system, positions are measured in latitude, longitude and height or altitude. There are a number of different celestial coordinate systems based on different fundamental planes and with different terms for the various coordinates. The spherical coordinate systems used in mathematics normally use radians rather than degrees and measure the azimuthal angle counterclockwise rather than clockwise. The inclination angle is often replaced by the elevation angle measured from the reference plane. Elevation angle of 0 is at the horizon. The concept of spherical coordinates can be extended to higher dimensional spaces and are then referred to as hyperspherical coordinates. Definition: to define a spherical coordinate system, one must choose two orthogonal directions, the zenith and the azimuth reference, and an origin point in space. These choices determine a reference plane that contains the origin and is perpendicular to the zenith. The spherical coordinates of a point P are then defined as follows. The radius or radial distance is the Euclidean distance from the origin O to P. The inclination is the angle between the zenith direction and the line segment OP. The azimuth is the signed angle measured from the azimuth reference direction to the orthogonal projection of the line segment OP on the reference plane. The sign of the azimuth is determined by choosing what is a positive sense of turning about the zenith. This choice is arbitrary, and is part of the coordinate system's definition. The elevation angle is 90 degrees minus the inclination angle. If the inclination is 0 or 180 degrees, the azimuth is arbitrary. If the radius is 0, both azimuth and inclination are arbitrary. In linear algebra, the vector from the origin O to the point P is often called the position vector of P. Conventions: several different conventions exist for representing the three coordinates, and for the order in which they should be written. The use of to denote radial distance, inclination, and azimuth, respectively, is common practice in physics, and is specified by ISO Standard 80000-2, 2009. However, some authors use I for inclination and I for azimuth, which provides a logical extension of the usual polar coordinates notation. Some authors may also list the azimuth before the inclination, and/or use I instead of R for radial distance. Some combinations of these choices result in a left-handed coordinate system. The standard convention conflicts with the usual notation for the two-dimensional polar coordinates, where I is often used for the azimuth. It may also conflict with the notation used for three-dimensional cylindrical coordinates. The angles are typically measured in degrees or radians, where 360 a degree equals A2 I rad. Degrees are most common in geography, astronomy, and engineering, whereas radians are commonly used in mathematics and theoretical physics. The unit for radial distance is usually determined by the context. When the system is used for physical 3-space, it is customary to use positive sign for azimuth angles that are measured in the counterclockwise sense from the reference direction on the reference plane, as seen from the zenith side of the plane. This convention is used, in particular, for geographical coordinates, where the zenith direction is north and positive azimuth angles are measured eastwards from some prime meridian. Unique coordinates, Any spherical coordinate triplet specifies a single point of three-dimensional space. On the other hand, every point has infinitely many equivalent spherical coordinates. One can add or subtract any number of full turns to either angular measure without changing the angles themselves, and therefore without changing the point. It is also convenient, in many contexts, to allow negative radial distances, with the convention that is equivalent to for any r, I, and I. Moreover, is equivalent to. If it is necessary to define a unique set of spherical coordinates for each point, one may restrict their ranges. A common choice is, Ra per mil 0 yen, 0 a degree a per mil currency Ia per mil 180 currency a degree, 0 a degree a per mil currency I 360 a degree. However, the azimuth I is often restricted to the interval. This is the standard convention for geographic longitude. The range, 0 a degree, 180 a degree for inclination is equivalent to, a 90 a degree, plus 90 a degree for elevation. Even with these restrictions, if I 0 or 180 a degree then the azimuth angle is arbitrary. And if r is 0, both azimuth and inclination elevation are arbitrary. To make the coordinates unique, one can use the convention that in these cases the arbitrary coordinates are 0. Plotting, to plot a point from its spherical coordinates, where I is inclination, move r units from the origin in the zenith direction, rotate by I about the origin towards the azimuth reference direction, and rotate by I about the zenith in the proper direction. Applications: the geographic coordinate system uses the azimuth and elevation of the spherical coordinate system to express locations on Earth, calling them respectively longitude and latitude. Just as the two-dimensional Cartesian coordinate system is useful on the plane, a two-dimensional spherical coordinate system is useful on the surface of a sphere. In this system, the sphere is taken as a unit sphere, so the radius is unity and can generally be ignored. This simplification can also be very useful when dealing with objects such as rotational matrices. Spherical coordinates are useful in analyzing systems that have some degree of symmetry about a point, such as volume integrals inside a sphere, the potential energy field surrounding a concentrated mass or charge, or global weather simulation in a planet's atmosphere. A sphere that has the Cartesian equation x2 plus y2 plus z2 equals c2 has the simple equation r equals c in spherical coordinates. Two important partial differential equations that arise in many physical problems, Laplace's equation and the Helmholtz equation, allow a separation of variables in spherical coordinates. The angular portions of the solutions to such equations take the form of spherical harmonics. Another application is ergonomic design, where r is the arm length of a stationary person and the angles describe the direction of the arm as it reaches out. Three-dimensional modeling of loudspeaker output patterns can be used to predict their performance. A number of polar plots are required, taken at a wide selection of frequencies, as the pattern changes greatly with frequency. Polar plots help to show that many loudspeakers tend toward omnidirectionality at lower frequencies. The spherical coordinate system is also commonly used in 3D game development to rotate the camera around the player's position. Coordinate system conversions: as the spherical coordinate system is only one of many three-dimensional coordinate systems, there exist equations for converting coordinates between the spherical coordinate system and others. Cartesian coordinates: the spherical coordinates of a point in the ISO convention can be obtained from its Cartesian coordinates by the formulae. The inverse tangent denoted in I equals arctan, yx, must be suitably defined, taking into account the correct quadrant of. See the article on Arctan 2. Alternatively, the conversion can be considered as two sequential rectangular to polar conversions, the first in the Cartesian z-Euro-y plane from 2, where r is the projection of r onto the z-Euro-y plane, and the second in the Cartesian z-Euro-y plane from 2. The correct quadrants for I and I are implied by the correctness of the planar rectangular to polar conversions. These formulae assume that the two systems have the same origin, that the spherical reference plane is the Cartesian z-Euro-y plane, that I is inclination from the z direction, and that the azimuth angles are measured from the Cartesian x-axis. If I measures elevation from the reference plane instead of inclination from the zenith, the arc cos above becomes an arc sine, and the cos I and sin I below become switched. Conversely, the Cartesian coordinates may be retrieved from the spherical coordinates, where RA, 0, A, IA, 0, I euro, IA, 0, 2 I euro, by geographic coordinates. To a first approximation, the geographic coordinate system uses elevation angle in degrees north of the equator plane, in the range of 90 a degree per mil currency IA per mil 90 currency a degree, instead of inclination. Latitude is either geocentric latitude, measured at the Earth's center and designated variously by I, Q, IA euro squared, IC, IG, or geodetic latitude, measured by the observer's local vertical, and commonly designated I. The azimuth angle, commonly denoted by I, is measured in degrees east or west from some conventional reference meridian, so its domain is a 180 a degree per mil currency IA per mil 180 currency a degree. For positions on the Earth or other solid celestial body, the reference plane is usually taken to be the plane perpendicular to the axis of rotation. The polar angle, which is 90 a degree minus the latitude and ranges from 0 to 180 a degree, is called colatitude in geography. Instead of the radial distance, geographers commonly use altitude above some reference surface, which may be the sea level or mean surface level for planets without liquid oceans. The radial distance R can be computed from the altitude by adding the mean radius of the planet's reference surface, which is approximately 6,360 AA plus or minus A11 a km for Earth. However, modern geographical coordinate systems are quite complex, and the positions implied by these simple formulae may be wrong by several kilometers. The precise standard meanings of latitude, longitude and altitude are currently defined by the World Geodetic System, and take into account the flattening of the Earth at the poles and many other details. In astronomy there are a series of spherical coordinate systems that measure the elevation angle from different fundamental planes. These reference planes are the observer's horizon, the celestial equator, the plane of the ecliptic, and the galactic equator. Cylindrical coordinates. Cylindrical coordinates may be converted into spherical coordinates, by the formulas. Conversely, the spherical coordinates may be converted into cylindrical coordinates by the formulae. These formulae assume that the two systems have the same origin and same reference plane, measure the azimuth angle I in the same sense from the same axis, and that the spherical angle I is inclination from the cylindrical z-axis. Integration and differentiation in spherical coordinates. The following equations assume that I is inclination from the z-axis, the line element for an infinitesimal displacement from to is. Where are the local orthogonal unit vectors in the directions of increasing, respectively, and are the unit vectors in Cartesian space? The surface element spanning from to and to on a spherical surface at radius is. Thus the differential solid angle is. The surface element in a surface of polar angle constant is. The surface element in a surface of azimuth constant is. The volume element spanning from to, and to is. Thus, for example, a function can be integrated over every point in a 3 by the triple integral. The del operator in this system is not defined, and so the gradient, divergence and curl must be defined explicitly. Kinematics. In spherical coordinates the position of a point is written. Its velocity is then. And its acceleration is. In the case of a constant or, this reduces to vector calculus in polar coordinates. See also, celestial coordinate system, del in cylindrical and spherical coordinates, elevation, Euler angles, gimbal lock, hypersphere, Jacobian matrix and determinant, list of canonical coordinate transformations, sphere, spherical harmonic, theodolite, vector fields in cylindrical and spherical coordinates, yaw, pitch and roll, notes. Bibliography, Morse P.M., Fespch Methods of Theoretical Physics, Part 1. New York, McGraw-Hill. PA 658. ISBN A0-07-043316-X. LCCN A5211515 Margenau H., Murphy G.M. The Mathematics of Physics and Chemistry. New York, Devan Nostrand PPA 177 €178. LCCN A5510911 Korn G.A., Korn T.M. Mathematical Handbook for Scientists and Engineers. New York, McGraw-Hill PPA 174 €175. LCCN A5914456. Asin B000CKZX7 Sauer Sabacube die Mathematische des Ingenieurs. New York, Springer Verlag PPA 95 €96. LCCN A6725285, Moon P., Spencer D.E. Spherical Coordinates. Field Theory Handbook, including coordinate systems, differential equations, and their solutions. New York, Springer Verlag PPA 24 €27. ISBN A978-0-387-18430-2. External links, Haswinkel, Michiel, ed., Spherical Coordinates, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. MathWorld Description of Spherical Coordinates, Coordinate Converter. Converts between polar, Cartesian and spherical coordinates. Spherical Coordinates Animations illustrating spherical coordinates by Frank Wattenberg. Conventions for spherical coordinates. Description of the different conventions in use for naming components of spherical coordinates, along with a proposal for standardizing this.